Okay, so this is what we started last lecture, multi-stage compression, right? So what is the need of multi-stage compression? There was some limitations for the single stage compression. What limitations are there? So it requires very heavy parts if you are employing same compressor for higher pressure ratios. Like single stage compressor limitations are like 0 to 6 bar or 7 bar. तुम्हाला 10 bar च्या वर जायचं असेल तर त्या केस मध्ये if you try to build a bigger compressor with bigger piston, cylinder head, all that, so it increases the weight. Also, it causes the balance problems in the compressor, high torque fluctuations, and it becomes very heavy flywheel for the installation. So it is very not feasible solution. So that is why we go with the multi-staging. So what is multi-staging? So air is compressed in multiple stages. So that is why the name is multi-stage compression. So you can see here the diagram is here. Air is taken inside. So this is a starting of suction. So air is at pressure P1, temperature T1. Now first it is compressed at low pressure. So low pressure compression. So pressure increases to P1 to P2 and temperature from T1 to T2. Then we employ the intercooler. The intercooler that we'll see in the next PV diagram. Okay. But intercooler is used to reduce the temperature of compressed air. But just air compress करतो. So we all know that we increase pressure. Sit there. Why are you changing? Don't try to be over smart. So when we compress the air, its temperature increases, and we want to decrease the temperature. So that is why we employ the intercooler. After intercooling, the pressure is same in intercooler. It is a constant pressure heat rejection process. Then this P2 T1. So theoretically or ideally, this temperature after cooling should be equal to T1. That is the suction temperature. Then this is again passed through intermediate pressure compressor, where it is compressed to P3 pressure and temperature increases to T3. Again, it is passed through intercooler. Then we get the same pressure P3, but temperature is reduced to T1. Again, it is compressed in the last stage, high pressure compression, and then we get the final pressure, that is P4 and temperature T4. Okay. So we'll see a short animation video for this. So it has an electric motor which is connected to a compressor shaft. So this is a single acting or single stage compression. This is the classification we have already seen. So this is a reciprocating air compressor piston, and this is a cylinder. Then there is this crankshaft is there. This is a connecting rod, and this is crank. Inlet valve, suction, then compressed air, then outlet. So this is a discharge valve. This is the indicator diagram, actual indicator diagram. Okay, 1 to 2 that way. टेन बार पर्यंत सिंगल स्टेजचं आपण डिस्चार्ज प्रेशर मिळवू शकतो. Then second is multi-stage. So we have first stage, second stage, and in between we have intercooler. It's a low pressure. It's intercooler, then it enters to high pressure. We can achieve pressures up to 20 bars or 290 psi, pounds per square inch. So this is a diaphragm type of compressor. This is a vane type of compressor. These are the sliding vanes. This is all the grooves. So area changes along the periphery. So where area is less, here air is compressed and then it is different. So inlet, compress, and then exhaust, or sorry, discharge. Okay. So let us go back to the PPT. So coming back to the indicator diagram. So this is the indicator diagram for this multi-stage compression. So first case we have seen, that is single stage compression. So in single stage compression, if we employ, so indicator diagram will be regular, that is 1 to 8 to 5 to 7 to 1. So this is a regular indicator diagram for the single stage compression. Again, if you go with multi-stage or two-stage compression without intercooling, okay, without intercooling, what is its effect? Its diagram will be similar to single stage. Its diagram will be 1 to 2 low stage compression, then 2 to 8 high pressure compression, then 8 to 5 delivery of compressed air, 5 to 7 suction, 7 to 1 intake of atmospheric air. Then we have two-stage compression with intercooling. Now we have an intercooler between the two compressors. So in that also we have two cases: perfect intercooling and imperfect intercooling. Perfect intercooling means काय? So this is again the schematic. This is a low pressure compressor, intercooler, and high pressure compressor. So we have P1 T1 intake. Here we have P2 T2. It is cooled to T3, and then it is compressed to P3 T4. Okay, similar to previous one. Now in perfect intercooling, the outlet temperature of compressed air after intercooler, that is T3, it is equal to T1. So that is why the name is given perfect intercooling. So at this case, we require very less work. Then comes an imperfect intercooling. In this case, this T3 is greater than T1. Okay. So coming back to the indicator diagram, for the perfect intercooling, what was the diagram? 1 to 2. Then because of intercooling, it goes 2 to 3. Then 3 to 4 is a high pressure compression. Now you can see previous for two cases, indicator diagram was 1 to 8 to 5 to 7. Now because of intercooling, there is a saving in the compressor work. So this much amount of work is saved. So that is why yesterday we have said that with intercooling, not only temperature of air decreases, but also there is a saving in the compressor work. Okay, that is the beauty of intercooling. Then we saw the formulas for each case. Then we discussed what is the criteria for minimum work required. So for that, we discussed the maxima and minima concept. So for diploma people, this concept I'm very much in doubt that you might be knowing. So that is why yesterday we discussed. So whenever you discuss a function, there always will be one global maxima, that is global maximum value, and there will be always global minima, that is global minimum value. But if you take a short range like this in between some 2 points, there will be some local minima, sorry, maxima, and there will be one local minima, local maxima, local minima. Here our objective is to find out global maximum and global minimum. For that case, you have to take the derivative and equal it to 0. Why we are taking derivative and equal to 0? Taking derivative म्हणजे काय असतं? We are calculating the slope of the tangent. Okay? म्हणजे तुम्ही जे आता 10वी किंवा डिप्लोमा मध्ये पण शिकला असता इंटिग्रेशन आणि डेरिव्हेशन. ते काय असतं मोस्टली? डेरिव्हेशन म्हणजे काय असतं ते तुम्ही कुठल्याही पॉइंटला एक टँजंट काढा, त्याचा जो स्लोप असतो दॅट इज गिवन बाय dy by dx. इंटिग्रेशन म्हणजे काय असतंय? इफ यू वांट टू कॅल्क्युलेट एरिया अंडर दिस कर्व, so that is why you take the integration. So that is the physical meaning of integration. बऱ्याच पोरांना सगळं माहित असून पण त्याचं फिजिकल meaning माहित नसतं. ठीक आहे? डेरिव्हेशन मध्ये काय असतं? You draw a tangent at any point and you calculate the slope by derivation. इंटिग्रेशन म्हणजे काय? You calculate the area under the curve. च्या अंडर जो कर्वच्या अंडर जो एरिया आहे, you want to calculate it, then you have to do the integration. Okay? So we took the derivative of the indicated power with respect to intermediate pressure P2 equal to 0. So by this way we'll get either maxima, global maxima or global minimum. So then we solve the derivation and the final result is intermediate pressure P2 should be equal to square root suction pressure into discharge pressure. So that is the criteria for minimum work, right? Then we saw the work required in the both the cases. The minimum work that is required in 2 stages. This is the formula. In 3 stages, minimum work required is this formula. So at this point, I think we stop in the last lecture. So today we'll continue our quest in the reciprocating air compressors. Okay. So we'll solve one numerical. Okay. So example of 2-stage reciprocating air compressor with intercooling. Write down. A 2-stage compressor compresses air from 1 bar and 20 degrees Celsius to 42 bar. If law of compression is PV raised to 1.35 equal to constant and intercooling is complete to 20 degrees Celsius, find per kg of air, work done in compressing air or indicated power, and mass of water necessary for abstracting or absorbing heat in intercooler. The temperature of cooling water is 25 degrees Celsius. Okay. If the temperature rise of cooling water is 25 degrees Celsius, this is temperature rise. Okay. So in this case, they have given you the suction pressure, that is 1 bar, suction temperature T1 is given 20 degrees Celsius. They have given you the discharge pressure P4 as 42 bar. They have given you the law PV raised to 1.35. Also, this is a case of perfect intercooling. That is, T3 will be equal to T1, and you have to calculate work done. That is indicated forward. So one by one, we'll solve it. So if you see the formula for work done or work required in compressor multi-stage, we required all of the three pressure values P1, P2, and P4. But here only P1 is given 1 bar, P4 is given 42 bar, P2 we have to calculate. Now we have seen for the perfect intercooling, what is the criteria? P2 should be equal to square root P1 into P4. So that way we can calculate P2 and then we can calculate work done. For this case, we'll see in the next slide. So this is a indicator diagram for this given case. 1 to 2 low pressure compression, 2 to 3 intercooling, 3 to 4 high pressure compression, 5 to 6 delivery of compressed air, 5 to 7 again suction and intake of air 7 to 1. Okay. This is a schematic of the given case. Low pressure intake is 1 bar, 20 degrees Celsius. Then we have here perfect intercooling. Then we have high pressure and output is 42 bar. So draw both the diagrams so that your understanding will be clear. Now here they are given perfect intercooling. So that is why this isothermal line will pass through point number 3. So dotted line will pass through point number 3. So no need to draw this 0.8 and this hash region. This is just shown that this is the amount of work we can save. So just draw 1 to 2 to 3 to 4 to 5 this way. Okay. Draw both the diagrams. The schematic also you draw so that you understand what is happening. Indicator diagram also you draw. So in given example, it is given that increase in temperature of cooling water. So this is a intercooler. Cooling water comes from this side, cooling water in, cooling water goes outside from this. So cooling water out. So while heat exchange, the temperature of cooling water increases by 25 degrees Celsius. So that is given in this case. Okay. So P1 is given 1 bar, that is 1 into 10 to the power 5 Pascal. T1 20 degrees Celsius, 293 Kelvin. P2 is given 42 bar. Increase in cooling water temperature is 25 degrees Celsius. So here, first we'll calculate the P2 and then we can calculate work done. So here P2 will be equal to, for perfect intercooling, P2 is equal to under square root P1 into P4. So this will be under square root 1 into 10 to the power 5, 42 into 10 to the power 5. Calculate the P2. Dakshata Khare, okay, 648. Good. Or 6.5, we can say 6.5. 6.48 comes, right? Where is Dakshata? She is attending online. 6.48 bar. Okay. Correct. Okay. Now we want to calculate the work required. What is the formula for two-stage indicated power? N upon n minus 1 into P1 V1 is equal to, or into in bracket P2 by P1 raised to n minus 1 upon n plus P4 by P2 raised to n minus 1 upon n minus 2 bracket complete. So here instead of P1 V1 you can write MRT1 also. So instead of P1 V1 you can write MRT1 also. M, it is given like per kg, so M will be 1, R is 287 and T1 is 293. So no need to calculate this volume. Directly you can write here MRT1 also and put the value. So both way the value will be same. P1 V1 or MRT1, both are same. Put all the values. N is 1.35, so into mass is 1 into 287 into 293 into in bracket P2 by P1 6.48 divided by 1 raised to this plus P4 by P2 42 divided by 6.48 raised to this minus 2. Calculate and tell me the answer. Asbe 6.48. Okay. So how much is the indicated power? Average is 385.9. So others take how much? How much you are getting? Dange, how much? कैसे आणला का तुम्ही दाखवा? Okay. How much you are getting? New member, first bench. Kelsey, where is your Kelsey? Huh? Hostel. So afternoon you please bring. Huh? This one. Huh? How much you got? I am Gar. $385.87. Okay, so how much you got? How much you got? One single stage मध्ये काढा कॅल्सी मध्ये. कसं काय? कसं नाही काय? How this online students have calculated? Calculate in the mobile that yes. Mobile मध्ये येत नाही का? Calculus. तुम्ही फर्स्ट बेस तुम्ही डाउनलोड करा त्या कॅल्क्युलस करून घे, त्याला सांगा प्ले स्टोअरला आहे. How much? Or at least you calculate outside bracket as another value, then you calculate inside bracket and then you multiply both. That way you can proceed. Calculate outside bracket first. That n upon n minus 1 into p1 that you calculate separately, write down, and then you multiply by inside calculator. 5.25. Students are getting how much? 4.38. How much? In bar you pay. I am getting on mobile. What is the problem? 4.04. On mobile you can try. In one stroke I have got the answer. So, okay. So here work done is around 4 bar, or work required indicated power is, sorry, not bar, 4 into 10 to power 5 joules per kg. 4 into 10 to power 5 joules per kg, correct? Or 4.04 into 10 to power 5, right? So everybody got around this, around 4. So in chat also people are getting around 4.04, correct? Yes, that side. South. Sudhir Raut. Got the answer? Show me. You are getting 4 into 10 to power 5 approximately. How much you got? Kilojoule. Kilojoule per kg. Or you can say 4 into 10 to power 5. Or you can say 0.4 megajoule per kg. Anything you want. Okay. So I hope everybody got the same answer. Now next part is calculate the mass flow rate of water in the intercooler. So this is a schematic of intercooler. This is a pipeline for the cooling water. Cooling water comes from this side, it goes out from this side. Then comes the hot air in, and this is the hot air out. So heat exchange takes place between these, right? So whatever heat lost by hot air, that is the heat gained by cool water, correct? So if you apply the law of conservation of energy here, heat lost by cooling, hot air is the heat gained by the cooling water. So here by law of conservation of energy, that is the first law of thermodynamics, heat gain by cooling water is equal to heat loss by hot air. So how to calculate heat loss or heat gain? MCP delta T. So that is the standard formula. MCP delta T, mass flow rate into specific heat into change in temperature. So mass flow rate of water into its specific heat value into change in temperature of cooling water into mass flow rate of air into specific heat of air into delta T. Delta T means change in temperature, T2 minus T3. Correct? T2 was incoming air temperature, T3 is outgoing air temperature. So here M3 mass flow rate of water is unknown, but we know the specific heat of water, that is 4.187 into 25, that is the what given in this case rise in temperature of cooling water, is equal to mass flow rate of what air. We have taken 1 into specific heat of air is 1.005 kilojoule per kg Kelvin into T2 minus 293. So here we don't know the value of T2. So again we have to calculate here the value of T2. So write down up to this point. So I hope everybody knows the concept of specific heat. So here an illustration is given, like if I take a piece of iron, its temperature is 25 degrees Celsius. If I want to increase the temperature of this 1 kg of iron by 1 degree Celsius, amount of heat required is its specific heat. So heat required to raise the temperature of unit mass of a substance by 1 degree Celsius, that is its specific heat. Now, how to calculate T2? So, compression process is isentropic. For isentropic process, in last numerical we have seen there is a relation between temperature and pressure. So, T2 by T1 is equal to P2 by P1 raised to n minus 1 upon n. So, here T2 is unknown, but T1 is given 20 degrees Celsius or 293 Kelvin. P2 we calculated 648 divided by P1, suction pressure is 1 bar. So, from this calculate the value of T2. Calculate the value of T2. 475 point. Okay, I got around 475.50. Calculate. So how to calculate this in calci? Anybody facing any problem? This side, how to calculate this and he calculate कसं काढायचं आता तुम्हाला हे प्रश्न पडला असेल हे कसं काढायचं any problem? First bench, any problem calculating? How to calculate T2 from this? First calculate this 6.48 raised to this one. And then you multiply by 293, you will get T2. Dange, how much you got T2? 4? First bench, how much T2 you got? 475. Okay. So put this value of T2 into this equation, energy balance equation, and then you calculate the mass flow rate of water. Okay, so mass flow rate of water into this 475.58 minus 293. So from this calculate mass flow rate of water. 0.147. Okay. So you take in Kelvin. It is a difference. So it will be 25. You take difference, right? So I do the values. Okay, 25 and 50 degree Celsius. So Kelvin किती होणार? 25 किती होणार? 298. 50 किती होणार? 323. So the difference किती येतो? Same हो जाएगा. So please see here. What Aditi asking is that the temperature difference is given in degree Celsius. So why you are not converted into Kelvin? Okay. So it is a temperature difference. So if you take in degree Celsius or Kelvin, it will be same. So 1.75 is the answer. 1.75 kilogram. Okay. So see this numerical once again. I will explain. This was the two-stage reciprocating air compressor with intercooling, perfect intercooling. Okay, so this is a two-stage compressor with perfect intercooling. They given you the P1 and suction pressure 1 bar and discharge pressure 42 bar. They are given you T1 value. They have given you the change in temperature of cooling water. So here they ask to calculate work done. So there is a formula for two-stage compression. This one, all the values are given readily to you, but in this case P2 was unknown. So for perfect intercooling, the condition is P2 is equal to under square root P1 into P4. That way we calculate work required. For intercooler, we applied the law of conservation of energy, that is heat lost by hot air, that will be heat gained by cool water. So that way we applied. Here again T2 was unknown. We calculated by the law for isentropic processes, the relation between temperature and pressure. Okay. So we'll solve another example. Let us see how many of you are able to solve this. Again, nothing new or nothing twist is there in this example. Plain example it is. You have to use the formulas and calculate the required entities. So I'll read it for you. A single stage double acting air compressor is required to deliver 14 meter cube of air per minute and measured at 1.03 bar and 15 degrees Celsius. The delivery pressure is 7 bar and speed is 300 RPM. So it is a single stage. Okay, it is not multi-stage, single stage, but it is double acting. Okay, it is double acting. So the delivery pressure is 7 bar and speed is 300 RPM. The VC is given. Clearance volume is 5% of VS with N is equal to 1.3 for both expansion and compression. Calculate VS, swept volume, T2 delivery pressure, temperature, and indicated power. Okay. So see here, this is a double acting compressor. That means if this is a piston cylinder assembly, right? So piston will compress the air on both sides. So इकडे पण compress करणार, मग इकडे पण एक suction discharge wall असणार, and it will discharge or compress the air on this side also. So here again it will be suction wall and there will be a discharge wall. So this way the piston will act. It will compress on the both sides of the cylinder. So in this case, we take the speed as 2n. So in last lecture, I have told you, n for single acting, it is n, and n for double acting. So this is a single acting cylinder. N is equal to 2n for double acting. N is RPM. Okay. So write down the given data. So one by one, we'll write down the given data. In this case, how much amount of air is required to deliver? 14, right? So volume, flow rate, here it is 14 meter cube per minute. Again, they have given suction pressure. P1 is given 1.013 bar. They have given a T1, that is 15 degrees Celsius or 288 Kelvin. Delivery pressure is given, that is P2, that is 7 bar, and N is given 300 RPM. In this case, VC is 5% of VS, or VC by VS is 5%, or we can write down it as a 0.05. Okay, and the index for expansion or compression, it is 1.3. Here we have to calculate VS, that is swept volume, T2, that is delivery temperature, and IP, that is indicated power. Okay. So how to calculate? Okay. So here we have a formula for volumetric efficiency. What is the formula for volumetric efficiency? It is a fresh air delivery divided by swept volume. Another formula is this. What? Another formula for 1 minus K. 1 upon n minus. Okay. So what we'll do, first we'll calculate the volumetric efficiency from this formula, because everything is given. They have given n, they have given P2, P1, and K is also given. What is K here? K is 0.05. That is the volume ratio or clearance ratio. After we calculate volumetric efficiency, here the fresh air delivery is given 14 meter cube per minute, and then we can calculate swept volume VS. So calculate volumetric efficiency. So 1 minus K is 0.05 into bracket P2 is how much? 7 divided by 1 raised to 1 by 1.3 minus 1. So calculate volumetric efficiency. Dakshata is saying 0.82. 0.82? Okay, 0.82. So what we'll do, we'll put this into this equation. Again, we'll calculate fresh air delivery. It is given in this case, that is 14 meter cube per minute. So this way we can calculate the swept volume. So 0.82 will be equal to 14 divided by swept volume, that is Vs. Now calculate Vs. So 17 point meter cube per minute. Thank you. Door close. Thank you. Door close. Right. So this is answer number 1. They have asked to calculate Vs. Next we have to calculate T2. How to calculate T2? So for isentropic compression, we know the relation between temperatures. T2 by T1 is equal to P2 by P1 raised to n minus 1 upon n. Correct? Is it correct? The last numerical we have solved here, n minus 1 upon. So now we put the values. T2 is unknown, but T1 is known. How much is T1? 288, 15 degrees Celsius. Is equal to 7 divided by 1 raised to 1.3 minus 1 divided by 1.3. So from this calculate T2. Four Kelvin. Kelvin, na? Okay. So here pressure. Okay. So can you recalculate 1.013? Okay, so here pressure is 1.013. Okay, sorry. Right. And next, what we have to calculate here? Indicated power. So let us calculate. So here first we calculate the compressor work. What is the formula? N upon N minus 1 for single stage. What is the formula? P1 V1. RNI P2 by P1. N minus 1 upon N minus 1. So everything is given in this case 1.3 divided by 1.3 minus 1. Pressure P1 is 1.013 into 10 to the power 5 Pascal. Volume is given 14 meter cube per minute. 14 divided by 60 in brackets 7 divided by 1.013 bracket raised to 1.3 minus 1 divided by 1.3 minus 1. So calculate the compressor work and then we'll calculate the power. Calculate the compressor work. $160. Okay. 160 watts. Everybody's getting same 160. No. 57.58. How much? Ah, 57.58, correct? Everybody check your answers. So power, last time I told you, power is equal to compressor work into RPM. Now this is a double acting cylinder. So for double acting cylinder, or double acting reciprocating air compressor, this NW is equal to 2 times RPM. So power is equal to WC into 2 into N. So here calculate the power. The power is equal to compressor work is 57.58 into 2 into how much is the RPM? 300 RPM. So calculate this. This will be power in watts. That is RPM na, per minute. Here again we have to divide by 60. नाही जूल कसं आहे ना पर मिनिट आहे ना इथं by second आहे. So this is in watts. This is kilo. Okay, नाही kilo joule नाही. It is per second ना. So this value na. That is what I am telling. Here we have taken volume flow rate meter cube per second. So it will be joule per kg, joule per second. Joule per second is watt. We can take 57.58 kilowatt. Okay. Now here we have to divide by 60 in order to make it RPS. Then we'll get the power in watts. So this is again into 10 to power 3 here. Now you calculate. 5 आणि हे 10 इथंच 10 झाले मग काय ते परत तेवढं झालं परत or you can say 57.50 कॅल्सीची पण गरज नाही ह्याच्यात into 10 to power 4 correct watts or you can say चालतंय 575.8 kilowatt. So I hope everybody got the answer. So next we move towards the theoretical remaining part, that is the comparison of compressors, and then we can stop. Okay. Now we'll see one by one. So this is a table showing operating conditions of various compressors. Okay. थोड़ा maximize करू देगा क्या दिसते? Okay, so here see summary of typical operating characteristics of compressor in US. So they are compared. These are the compressors. They are compared with inlet capacity, that is in air CFM. Okay, this is ACFM, air CFM. Maximum discharge pressure is in PSIG. Okay, what is PSIG? Pounds per square inch gauge. So this is a gauge pressure. This is not absolute pressure. This is gauge pressure. Then we have volumetric efficiency is given. Efficiency, operating speed is given. RPM. Maximum power required to drive the compressor is given, and application where the compressor is used, that is given. So let us go one by one. First is centrifugal compressor. So its inlet capacity is 100 to 200 air CFM. The maximum PSIG is 10,000. Then efficiency here it is 70 to 87%. Operating speed RPM is 1800 to 15,000. That is the RPM, operating revolution per minute. Maximum power required is 50,000 horsepower or extra. Mostly it is used in process gas and air. Then we have axial. Axial has somewhat larger air intake capacity. It has also larger efficiency compared to centrifugal, and it is mainly used for air. Also, axial compressor require larger power. Then we have positive displacement compressor like reciprocating air compressor, rotary compressors, etc. Reciprocating air compressors have inlet capacity less compared to this. So this has 100 to 200,000, like 2 million, or sorry, 1 lakh to 2 lakh, 100 to 2 lakh CFM. Here inlet capacity is less, 10 to 20,000 CFM. Again, here maximum discharge pressure is higher compared to this, that is 60,000 PSIG. Then efficiency is highest compared to all, or somewhat good, 80 to 95%. Most it is used in air and process gases. Then we have diaphragm type, rotary screw dry, rotary lobe, sliding vane, and liquiding. So all these are compared here. So remaining rotary types, mostly they are used in process industries and air industries. Vacuum, for vacuum service, in that case we go with the sliding vane and liquiding. So which one is having highest efficiency? Mostly we can say axial type and reciprocating air type is having highest efficiency. Which one requires maximum horsepower? That is a centrifugal type requires the, axial type requires the maximum horsepower compressor work. So this is just a comparison between different compressors that is given. This is again plotted on inlet capacity meter cube per hour versus discharge pressure, and their operating region is given. So graph showing operating regions of various compressors. So reciprocating air compressors lies, you can see here, from 10 meter cube per hour to 10,000. Sorry, not 10,000, up to, like, you can say 50,000 meter cube per hour, and its operating pressure is from 0 bar to about how much is this, 1,000 or what? Like we can say 50, not 55,000 bar. So up to that it can go. So it should not be in bar. This unit is wrong here. It should be in PSID or something like that. This way, every compressor is compared inlet capacity versus discharge pressure. Let us see some of the advantages and disadvantages. So first, we'll see centrifugal dynamic type, that is centrifugal and axial. Advantages of centrifugal is wide operating range. So it has wide operating range of pressure. It has high reliability compared to others. It has low maintenance. But it also has disadvantages. It has instability or reduced flow. So at low flow rates, it has stability problems. It is sensitive to gas composition change. So if there is some bubbles formation, or not bubble formation, if there is a change in composition of gas, molecular change, molecule level change. So it is sensitive. Okay. Then axial, it has high capacity for given site. It is having highest capacity actually. Then high efficiency, heavy duty, and low maintenance, but it has a low compression ratios and it has limited turnaround. So limited time we can use this axial compressor. Then we have next positive displacement type. In that we have reciprocating, diaphragm, and screw type. Reciprocating is having again wide ratios, high efficiency, but it has heavy foundation required. Flow pulsation, that means flow pulsation म्हणजे सेंट्रिफ्युगल मध्ये कसं कंटिन्युअसली तुम्हाला एअर फ्लो रेट मिळतो, पण ह्यात कसं होतं की एकदा सक्शन आहे, एकदा डिस्चार्ज आहे, त्याची एक वेव्ह मध्ये तुम्हाला एअर डिलिव्हरी मिळते. तसेच सेंट्रिफ्युगल मध्ये तुम्हाला कंटिन्युअस एअर डिलिव्हरी मिळते. रेसिप्रोकेटिंग मध्ये तुम्हाला एकदा डिस्चार्ज येतो, थोड्या आणि परत सक्शन साठी थांबावं लागतं, परत डिस्चार्ज, परत सक्शन, असं ते पल्सेशन्स बघायला मिळतात. Then it has having high maintenance because of all these reciprocating parts, piston and all that. It has high maintenance. Then we have diaphragm type. It is again very high pressure, low flow, and low moving seal. But because of that elastic part in diaphragm, it has some maintenance problems. Then screw type, wide application, high efficiency, high pressure ratio, but it is kind of expensive because it is complex in design and it is unsuitable for corrosive or dirty gases. Wherever corrosion is there, you cannot use screw type compressor. So this is just a comparison between different compressors, their advantages and disadvantages. So thank you. So with this chapter is completed. Let us recap whatever we have done in this chapter. In this chapter, we started with compressor. What is compressor? Classification of compressor. Okay, what is the major classification of compressor? Positive displacement type and dynamic type, right? Then we saw the working of reciprocating air compressor, right? Then we saw indicator diagram, PV diagram. Then we derived the equation for indicated power, that is WC. Then we saw some numericals for that single stage compressor. Then we started multi-stage compression, multi-stage with intercooling. We started in that we saw perfect intercooling. We saw the condition for minimum work. So for minimum work, the P2 intermediate pressure should be equal to under square root P1 into P4. Again, we saw all the numericals related to multi-stage, and lastly we saw numerical again related to single stage but double acting cylinder or reciprocating air compressor. So for online examination, in that point of view, I will give you the quiz now. I will put it on our group, so you will solve it. Okay. So those are in online. Put your attendance in the chat box, and I will give you the test. So kindly attend the MCQ test. Total 35 questions are there. For each, I have given you 30 seconds. 30 seconds pass का एक minute दो. Huh? Okay, so we'll change the timing. Okay. 1 minute बस. Okay, so I will put the quiz in the chat box. Try to solve it. Also, I will put the quiz on our group also. So from that also you can. Okay. With this, we'll stop here. Thank you.